Okay, welcome to session number 4 of the course. And I would like to prepare today by showing you applications in the area of cubic polynomials and translation invariant linear mappings from cubic polynomials to cubic polynomials for the main goal, which is to represent BIBOS systems as convolution operators with bounded measures. All these terms will be explained during this course, maybe today and at least next time. But for me, the system of the vector space of cubic polynomials is a very nice object because the objects are really continuous functions. Well, they're unbounded, but this doesn't matter. They are forming a 4-dimensional space with the monomials. And we have seen that the monomial basis can be chosen in the mathematical spirit, which means 1x, x squared, x third power, or in the decreasing order as it is customized for the polyval routine of MATLAB. So I would like to use that order and talk about polynomials in this way. First, I would like to recall that for every linear mapping between two finite dimensional vector spaces, there is a matrix representation. The matrix representation is nothing else, but instead of storing all the possible values for all the possible vectors, which is of course impossible, we are storing just for one fixed basis the elements under the operator. If you have a basis with n elements, you have to store n column vectors in the target space. So if the mapping is going from Rn to Rm or Cn to Cm, we are coming up with a real or complex m times n matrix standard conventions. M is the height, n is the width. Now, once you store the information and you concatenate operators, of course, this is only possible if you are following the domino principle, which I mean, you map the target space and of the first operator has to coincide with the domain of the second operator. And then you have to come up with a kind of multiplication of the matrices. And this is what we know, the well-known scheme of matrix multiplication. Actually, I should go back and I should recall to you, matrix multiplication is just applying a vector B to all the columns of the matrix R in order to get B combined with A. Now, why has this been mentioned now? Because we will see that if the operator is translation invariant, you can store the information about the linear mapping even in a more compact form. You don't have to do a 4x4 matrix, but we will do also this. But you can store it with just 4 components, which are the components describing elements of the dual space. So the most important message for this course is signals are cubic polynomials. They are isomorphic to R4, and you can think of column vectors, but this is not important. You should think of functionals as something that can be described by ways of row vectors. But again, this representation is not relevant. You should think of very concrete things. Now, with GeoGebra, I have described last time that you can do such an experiment where you are doing derivatives or shift operators, and all these things commute with translations. So if you take a derivative of a curve, which is a cubic curve, you get a parabolic curve. And if you shift the original cubic curve, also the tangent, which has this behavior, will move accordingly, so by the same amount. The same is true if you shift everything by 5. Of course, you can shift other thing. The shift by 5 commutes with any other shift. 5 plus 3 is 3 plus 5, and that's why everything works. So we will work with the space of cubic polynomials and with the MATLAB convention where everything is in decreasing order. This will be important for the description of the matrices that we will look at today, because the first column will contain the information about the target, the output of x to the third power under some of these systems, as I will call them. And the description in the first column will start with the cubic term at the top of the matrix. Now, as we will need it for the further description, you will have a space which is translation invariant, so it makes perfect sense to talk about the mappings from cubic polynomials to cubic polynomials which are commuting with translation. So we are looking at linear measurements. Okay, sorry. We also have to look, we need, for the description, we will need linear functionals, which are of having this property that they are compatible with linear combinations. Now, the examples that we have, and you have them in the notes, are point evaluation at 0, which is the most important one, or the derivative at some point x, or an integral, or a weighted integral, or a Riemann-Stieltjes integral. All these terms are possible linear functionals. So it looks as if there were huge amount of linear functionals, but at the end, it's just a four-dimensional space. We don't have to discuss it here. Important fact, linear functionals can be, again, scaled and added up, so you can have linear combinations. So in order to recall, we will have this convention. Every polynomial in the space of cubic polynomials will be viewed as something having coordinates b1 up to b4. Now, I'm not sure if I've mentioned this already, but maybe it's a good repetition. If we look at linear operations, it could be a shift operator, a rescaling operator, a derivative. Then you get the matrix representation, a 4x4 matrix, because the basis has 4 elements, by looking at what happens under the operator by doing a shift. So if we do a right shift, and you remember, a right shift means replacing the argument x by x minus 1, because the new function, which is shifted version to the right, takes the values one step from the left. Now, if you go and ask what is x to the third power shifted to the right, you will find out it's x minus 1 third power. And we all know the binomial theorem and says it's, and now I'm looking at the first column, it's 1 times x third power minus 3 times x squared plus 3x minus 1. So this explains the coefficients in the first term. And of course, x squared goes to x minus 1 squared, which is x squared. So no cubic term, 0 cubic terms, 1 times x squared minus 2x plus 1, and so on. So this is a right shift matrix. And the inverse of this matrix, you can see it quickly, either by saying, well, clearly the inverse of the right shift is a left shift. So you have x plus 1, or you're computing it directly. And it's interesting to see that the triangular matrix form here has diagonal elements which are all ones. So the determinant is equal to 1, also inverse of the determinant is equal to 1. This is why an integer shift matrix has an integer valued matrix also for the inverse. Now, here you see what's happening with the stretching operator. X to the third, if you replace x by, let's say, r is 2, by 2 times x, then you have 2 times x to the third power, which is 8 times x third power. This is why you have 8, 0, 0, 0. Accordingly, x squared is going to 2x brackets, in brackets squared, which is of course 4 times x squared, and so on. And it's easy to check either directly by looking at what the operations are doing, that this matrix does not commute with this simple right shift, also of course not with the left shift, and therefore this is not an operator as we would like to see him. However, if you're looking at the differential operator, so you take the derivative of a function, mapping x to the fifth to 5 times x to the fourth power, and so on, then on the cubic space you have this operator. This commutes with the translation operator, and if you compute it in MATLAB, you can get the result, and you, of course, you can verify it by saying this is constructing the steepness of the tangent, and of course this moves with the graph of the function. Okay, so now we are looking at the special case because we will need linear functionals, and the linear functionals are linear mappings from Rn to the real line. Later on you can take Cn to the complex domain. So of course you're getting a row vector because the corresponding matrix is just consisting of a row vector which will have n components, so it's b1 to bn in an abstract description, but it's easy to find out because you just have to apply the linear operator, so in our case the linear functional, which I call sigma, to the first up to the last vector. As a typo, of course I will correct this later on. Now, the property that such a linear functional is compatible with linear combination says, if you apply sigma to a linear combination of unit vectors, namely the standard representation of a vector x with coordinate x1 to xn, then you can throw the sigma to the unit vector. So you get xk, the coefficients, times sigma of ek. So just setting sigma ek to be the b vector, you're coming up with the representation as a scalar product. So you know if you would do a representation of a scalar product in MATLAB, MATLAB doesn't have a scalar product command, you would take the vector b, turn it into a row vector. Actually in a complex situation you would take b prime, so it's conjugate. Then you have b1 conjugate, b2 conjugate, bn conjugate, scalar product with the column vector x1, xn, and that's exactly what you have to do here. So you see also here. Now, let me look at, again, a very specific representation of a very specific functional. And now you see the Dirac is not a mysterious function. It's a linear functional. It's a way of measurement, and you're measuring the polynomial function at the moment by applying the delta zero, which means you're picking out the value at zero. Clearly, this is a harmless linear procedure. And if you have the standard representation, it means just put x equals 0. The cubic, quadratic, and linear terms are disappearing, and so the last component is appearing. Of course, you can write b4, the number b4, as a scalar product of the horizontal unit vector number 4 against the vector b, and that's what we have to do. So if you are asking which row vector in the coordinate system of the polynomials written as column vectors is representing the delta zero, you have this here. And so for every other linear functional, you can just say, what are the coordinates that you have here? And you apply the functional to x to the third, x to the second, x to the x term, and constant 1. I think it would be a good exercise if you compute yourself the representing horizontal sequence or row vector for one of these other moving average operators. So maybe the first idea is that you choose h equal 1/2. So you take the average over the polynomial from -1/2 to +1/2. Or if you have a longer interval, say from -1 to +1, it's an interval of length 1, of length 2, of course, and you divide by 2 and so on. And for each of these linear functionals, you have a representation as a vector. You may, of course, ask yourself, if I have several measurements of a polynomial and all these measurements are with different values, h1, h2, h3, can it happen that they are linear independent? So is there a chance to reconstruct a cubic polynomial from 4 or 5 linear measurements of this kind? I leave it to you to think about it. Yes, here, just to make it easier for you to reproduce some of the experiments yourself, I was writing the differential operator, the MATLAB code, so it's essentially just the last line. You have to have a description of the derivatives of x to the power k, and you know it's k minus 1 with some factor. And so this just puts in the right position of the matrix the right number, and that's all. So that's how you can do the matrix representation, say, of the cubic polynomials, which means degree is 3, and derivative here. If you want to have the matrix for derivatives of order 2 and higher, you just take that matrix and take higher powers. We also know that if you do a differentiation, you are reducing the degree of a polynomial by 1. So if you reduce from a cubic polynomials, once you get quadratic, then linear, then constant, and from constant you get 0. So it's a so-called nilpotent operation, which means that one of the powers of this matrix is the 0 matrix. Next question that I would like to ask to you is, what can you say about the null space of this differentiation operator? What are the functions which have the property that the derivative, the cubic polynomials, such that the derivative is 0? I mean, the answer is quite obvious, and I think you should easily find out that this is a one-dimensional space, whereas if you're looking up linear algebra books on eigenvalues, you would like to have as many eigenvalues as you have eigenvectors. Here you have only one eigenvector, as I would say, but not the multiplicity of this eigenvalue, which is 0, is 4. So it's by far a problematic thing if you are looking for eigenvectors. So take a look at this maybe. If you are able to derive, where we've seen the binomial theorem more or less, the shape of a translation operator, then you can test whether your implementation is correct by looking at the fact whether it's true that A shift combined with B shift is the shift by A plus B. As a special case, take B equals minus A, and you get 0 shift, so the identity operator. Now, we have seen in the MATLAB experiment, in the GeoGebra experiment, that certain operations are obviously translation invariant. So whereas the blue curve is giving under some linear procedure the red curve, and you have it in the second line. So what I took here, just for illustration, is take the derivative. I have rescaled it so that you see it can be rescaled and also to get the nice picture, plus a shift to the left by 4 is giving you the red curve. Now if I replace the blue curve by the green curve, which means I do another shift on the original curve, and then I apply the same procedure, so again taking derivative over 5 and so on, I get the brown curve. So first of all, both derivatives, shift operators, linear combinations of these operators are translation invariant, and it's convincing without looking at the matrices by GeoGebra. You can look at the matrices, you will verify that everything is fine. Of course, MATLAB is never a formal proof, because you might be kind of having a situation where shift by exactly 1 is okay, but not by a square root of 2. But if you do it a few times and you see everything is fine, you don't have to go through the formal procedure. So yeah, and you know, I've taken as a standard polynomial in the cubic domain the polynomial which has zeros at -1, +1, the blue polynomial curve is -1, 0, and 1. So it means x minus 0 times x minus 1, which is giving the 0 at +1, times x plus 1, which is the 0 at -1. And by the standard rule, a minus b times a plus b equals a squared plus minus b squared. The second two brackets are x squared minus 1, and multiplied with x is just x third power minus x. So this polynomial has the representation a cubic term 1, no quadratic term 0, negative x, and 0 constant term. And you have this blue curve. Now, what we will demonstrate both by examples and by concrete, by abstract consideration is that in such a situation, if you have a mapping like this one, it's enough to know the output, not as a whole, but at the origin. So I have used the convention of saying P is the input, Q is the output, P of X is the input, Q of Y is the output. The claim is Y equals 0 is enough to have this knowledge. So if I want to emphasize that Q upon Q is the output, I write it as T of P. Sometimes I will leave out the brackets when it's clear. So this is a translation invariant system, and we are kind of approaching the idea that this impulse response, and why it's called like this will come in a moment, or will come later actually, is okay. So the formal statement is now this theorem number 1. Assume you have a linear mapping from the cubic polynomials to the cubic polynomials which commutes with translations. So either you're saying that the matrix representing the operation T commutes with all the translation matrices, or you're saying the concatenated operator is independent of the order. You can do it either way. Of course, you can rewrite it by taking the inverse of set to the left, that conjugating the operator T with the shift by set. So writing T minus set times T times set equals T. So it's invariant under certain manipulations, moving around this operator. And then the claim is, then there exists a linear functional, so something which maps cubic polynomials in a linear fashion into real numbers, in our case, in such a way that this linear functional sigma just has to apply it to the opposite shifted T minus Y of P. So if you were asking me, what is the value of the output signal, which I called Q of Y or T of P, the image of P under the system, at any point Y, I tell you, well, take your input polynomial, shift it by Y, so to say, in the opposite direction of the argument here, and then apply the functional. We will see that this expression actually means that we take the functional and move it along the time axis, but this comes later. I think, and I mentioned it here, that engineers probably would prefer to write, instead of the translation operator, to say, well, take P of dot plus Y. So T translation means you write minus Y, which is of course plus Y, as a function of a variable argument which is represented by the dot. And as a function of this dot position, you take it, you have a cubic polynomial, and you apply the functional to that particular polynomial. So each time you're asking for a new position, you get a new shifted version of your polynomial, which is the input function, and you apply the functional. Now, I would say that line number, or formula number 19, is one of the crucial things that you should be prepared to reproduce for the course. But it's not much more than applying the assumption in the smart way and getting familiar with the notations. So if I'm asking you, what is the value of a Q at Y? I see there is a small typo. Then I would say you should write Y as 0 minus Y. That's why we have the minus here. So what is missing here in this formula 19 is the argument, I'm writing it down, at 0. So I'm writing T of Y, then of T of P. This is a new polynomial, but at 0. So you're just saying, well, instead of focusing on the value of Q at Y, move the function in the direction so that the point of interest Y is becoming the origin. So we have a value at 0. So you're saying, well, take the input signal, apply your system, then apply the shift operator, and then the whole thing at 0. but we have assumed that t commutes with shift, any shift, so any concrete y is okay. So we can say we should do this here, which of course means now resolving brackets in the opposite direction. Well, first I have to take the input signal, position y, then the output signal, and of course what's coming out that has not changed is always to be taken at 0. But this is exactly the definition of our functional. If you look up here, the functional, no, it's how we define the functional. Yeah, we define the functional to be sigma is sigma of, I should, this also I have to write it better. I should write sigma of any polynomial, in this concrete case of ty of p, should be the value of the polynomial at 0. So by the definition, yeah, we have this representation. Now, the representation here just says, and I would like to leave it here for a moment, that whenever you're giving me a system, we can fabricate a linear, we can find a functional which has the representing property. But what is more important, or is equally important, is that this sigma is uniquely determined, and also that every such system can be represented in this way. And in the opposite direction, if somebody is giving you, so I'm reading the red formula number 18 from in the opposite direction, if somebody is giving you a linear functional and says, well, just take sigma at t minus y of p and define q of y in this way, then this will define a translation invariant linear operator. So you get all the operators in this way, and it's a one-to-one correspondence. So because this is only a motivation, we will do this in more detail later on with C0 and with continuous variables. Now, I have mentioned, and now that's why I want to do this, that we would like to define convolution. So it's clear, or it should become clear during this course, that convolution and Fourier transform are highly important terms, and they are arising natural in description of invariant systems. So essentially, every invariant system in real life is a convolution operator, in VAG terms, and every convolution operator can be turned into a multiplication operator by the Fourier transform. That's what you probably know. So I'm just trying to give you an idea how you could define the convolution of these linear functionals. So on the one hand, you've seen there are very concrete linear functionals. On the other hand, the convolution of these objects, which don't have to be represented by coordinates, is a quite fancy thing. And it's based on a very simple observation. Recall, when you have two matrices, they correspond to two linear mappings. If you compose two linear mappings, then you will have a linear mapping. Why? Because if you apply a linear mapping, let's say to x plus y, so to a sum, you're getting by the first a sum of the images, and then you apply the second linearity, you get the sum of the images under the composed mapping. And exactly the same way is happening here. So the composition of two linear systems will be a linear system. The composition of two systems which commute with translation, and that's a very nice exercise, which you should be able to come up with a one-line proof, is again an operator which commutes with translations. So also a composed operator where you apply T2 first and then T1 will be written with some sigma. Actually, as I mentioned already, for a uniquely determined sigma. So if somebody is giving you sigma 1, sigma 2, you can define the convolution by saying, okay, every linear functional defines by the rule which we had above, by this rule, an operator which commutes with translation. Take these two operators and make the composition, and then there will be some uniquely determined sigma. Now, there are many things that you can derive from this harmless basic observations. So at the moment, it's an abstract consideration. What about associativity of this new convolution? Normally, if you think of a proof for associativity of matrix multiplication, you have to deal with triple indices because you have two matrix multiplications, so you have two summations, and it's a mess. If you think of linear mappings, it's clear that the composition of linear mappings is associative. I like to explain to my students, if you take a train from Vienna to Salzburg, the usual way is, let's say, via St. Pölten and Linz. And one guy is saying, I was driving or going by train from Vienna through St. Pölten to Linz, and then I was continuing to Salzburg. The other guy was saying, well, I was first going to St. Pölten, and then I was continuing through Linz to Salzburg. Of course, you're always just describing a particular path from Vienna to Salzburg. So associativity for mappings is a harmless, obvious thing. And we're just imitating this by representing it. So this associativity is clear. Also, distributive law is quite obvious. You take one thing and you take a linear combination of two such functionals, you multiply out, so you take the star that we just have introduced in a harmless way. Also, scalar multiplication is harmless. You can either multiply the first or the second or the whole product, and you will get always the same. So this is something that you see often with tensors or so. But then, of course, the question is, what else could you ask for? And I was putting this online a little bit earlier. Maybe you have found yourself asking, what about commutativity? And convolution, as it is defined, usually is obviously commutative, but in this case, this is not coming for free. So it might be that we have a problem with the order in this commutation relation. So let's summarize what we have seen here so far. We are starting from the representation of any such linear operator on the cubic polynomials as a linear functionals. What was important is, if you look at point number 2, that here you have the shape of the functional, that it means the functional is take the input signal, apply the channel on it, so you have a new output signal. It's another cubic polynomials by assumption. And this cubic polynomial has a value at 0, and of course, evaluating at 0 is a linear function. So the composition is a linear system, then a linear functional is a linear functional defined on the input signal. And so with this, you are getting a representation, and you can read it both ways. If somebody is giving a sigma, you can define an operator, a matrix, and vice versa. We will see many examples later on and discuss in more detail. Once we have shown, and I have not done it here, that this representation is unique, we can define the multiplication of, or the convolution of functionals through as a multiplicative operation on these representing objects. And if you want, these are row vectors of size 4. It's a funny object. You have no direct rule if you describe it in those coordinates. But it's a nice operation. So you could try to do it by saying, well, if somebody is giving you the sigma, how can I build a matrix? Giving the other sigma, how can I build the other matrix? Do the matrix multiplication, how can I pull out this vector here? And of course, you have seen the sigma is just the constant term of the output if you apply the signal to the basis vector. So you apply t to x third power x squared x and constant 1. So if we go back to the matrix representation here, I go to this, maybe I have it once more elsewhere. Yeah, here, the differentiation operator, for example, is such an operator. You have just to take the sigma to be the row vector, which has 0, 0, 1, 0. So this is the representing linear functional. And yeah, this is one of the basic properties that we have. Now, we have a nice situation about the functionals. Now I would like to do a little bit more concrete thing, in the sense that I'm saying, well, the identity operator, or if you want the unit matrix, so I'm writing identity of P. You could also say it's a shift by 0, but okay, it's the identity operator. So how can we get the sigma? I'm writing now a subscript. So if you're giving me a system, a channel, I would like to produce the corresponding linear functional that's representing it. And the rule is, you're asking me, okay, what is the functional corresponding to the identity operator? Well, apply it to the polynomial P. Well, in this part, I'm sometimes writing P of X to please the engineers. Also, mathematicians would probably write just P, but it's just indicating it's an input signal. And the answer is the sigma, the action of sigma is apply the operator to the input signal, evaluate the output at 0. Now, clearly, identity operator applied to a polynomial is the polynomial, so I have to take the value of the polynomial at 0. And we have used the name for this functional. This is the Dirac impulse, the Dirac distribution, or the Dirac functional in our case. I hope there is no disturbing thing on your screen, but now it should be back. And now, so what you see here is that the identity operator corresponds, or the representing functional is the delta 0. I'm showing you the converse here now by saying, well, what if I want to know, it kind of is the converse true? I mean, I'm asking, maybe I should write in a different way. Is it true that the identity of P is coming out when I do my recipe? So I'm asking, is the first part, by this rule that we have established, take that linear functional and apply it to the polynomial, but shift it backwards. Okay, well, this shifted backwards polynomial with free argument is x minus y. So the t sub y means you're shifting in the opposite direction. Minus y is plus y. 0 plus y is just y. So yes, we are getting it back. So in this particular example, we're happy and see that everything is fine. So another definition, of course, would be, well, we define, and we will see that this is the only consistent prolongation of a shift operator from ordinary functions to generalized functions. But this is a bit far away, but the usual operation would be, I define abstractly at the moment a shift operator also to functionals. And it's kind of suggested by the simple functionals that we get by integration, suggests that one should define it in this way. Ty of sigma applied to P is obtained sigma at Ty of, that should be, of course, P, the same input argument. So what do you expect if you shift the Dirac at 0 to the position 5? So if you write as an engineer probably delta or delta 0 with the argument t minus 5, because that would move everything. That's exactly this definition, consistent with this definition. Now, if you're doing this or using this definition, then suddenly the famous shifting property of the Dirac delta, which is often thought as a fundamental statement in signal processing and written in a mysterious way, I'm overdoing it a little bit only, is becoming a harmless statement. So usually you find statements of this. The Dirac is this mysterious function which is 0 everywhere except 0. It has, very often people say it has the value plus infinity there. I'm asking myself, why not 3 times infinity or so? And it has integral equal to 1. From my point of view, at the moment, this is just making up hot air or using terminology. I will try to explain it in another way, but the claim is that if you do this delta and you shift it around and do this integral, you're getting f of y. So this is called the shifting property of the Dirac delta. Now for me, rewriting everything a little bit in our terminology, it means, okay, what is delta of t minus y? This is the y-shifted version of the delta 0. I've moved my delta from 0 to y by this formal argument. And then I'm doing integration, which means I applied to the function f. Now, the convention in the red box above 22 tells me this should be delta 0 at t minus f, which is f of, and we had this already above, this is f at y. And then the great thing about this shifting property is, if somebody asks you, what is the output under the identity operator? So kind of, how can you describe the values of the function or of the polynomial at every point? And the answer is just take the value at each of the points, because you're moving your Dirac about this. So in a way, it's not a very fundamental, but a rather mysterious description of the fact that a function is completely described by its values. You can reconstruct your function as a collection of all the values, but this has to be done in a specific and reasonable way. At the moment, the left-hand side is a formalism, the right-hand side is well established and can be justified by what we will do. I have already mentioned that invariant systems can be described by the invariants. I had minus set and plus set here now, let's say minus set is y. So it's if you conjugate the system by shifting before and afterwards, you have this here. So we have to see that we have operators on a space of continuous functions. All the cubic polynomials are continuous functions. The space has to be invariant. Therefore, because it's a linear space, it's meaningful to ask what are the operators which are linear from one space to another. Because in our case, it was four-dimensional, we could describe it by matrices. And then we can ask whether it commutes with translation or not. Here I'm just adding the comment, kind of what one would have to do if one does more details. I will do it later on for the continuous case, non-periodic case. If you're saying sigma of t is the functional representing the system t, then you give me a functional. And you can fabricate a channel or a system from this. And of course, this will be the original system. The same way is if you would give me any functional sigma, and then you fabricate a convolution operator, a moving average, I would say t is sigma. Then you have a translation invariant linear system that is having another linear functional, and you're coming back. So these two relationships simply say turning a system, representing a system by a functional and defining a system through a functional are inverse to each other as we have described it. And the way how we did it will be just exactly this. Now a little bit of the same kind, I skip the details here because you have them here, is what if I take not Dirac at delta but at t0? So that's the point evaluation at some point. So you see here the point evaluation is the delta at t0, or the Dirac moved to delta 0. And then with the same kind of arguments, you find out that the system introduced by the delta at 0 is just a shift. And what we have to observe is a shift by minus t. So that's why we are actually dealing here with moving averages and not with convolution operators. You know probably the relationship that convolving with the Dirac is shift by the amount which is in the argument. Now we have a minus. And this minus is a little bit nasty because it will require that we are doing a flip operator in the continuous domain, but well, that's how it is. We should not define a new convolution which is different from the old convolution. So we are very close with our assignment of linear functionals to systems and systems to linear functionals to the standard thing. Also, the convolution is correctly defined. because the flipped convolution product is the same as the convolution product of the flipped factors. But so you don't have to worry, you have the right convolution here, but at the moment you have not seen the explanation why you got the right convolution. But let us try at least to check what happens if you take the most simple functionals, which are these deltas. So what is the convolution product of delta at t1 with delta at t2? And the answer is, this is delta of t1 plus t2. And therefore it's the same as delta of t2 times convolved with delta of t1. So for Dirac measures, convolution is a commutative thing, and the answer is very simple. Once you have the red box above number 25, you know that convolution with delta is just a translation operator. So clearly the composition of two shifts by minus t1 and t2, independent of the order, is giving you a shift by minus t1 plus t2. And it's clear that the representing functional for this shift by sum of two values is the same as delta of t1 plus t2. So we have a very simple rule, which will be also very useful and the basis for the understanding of convolution of more general systems, and also the basis for the argument for commutativity. Maybe I'm just going here to the dark blue text. If you're looking at a functional which is a finite linear combination of deltas, then of course any two of them are commuting with any other of the same kind. And by taking limits, we will achieve the same property for arbitrary Bibos systems. So whereas it's not clear from the beginning, at the end it's clear that they will commute, which has a lot to do with the fact that there are common eigenvectors. And the eigenvectors will be the pure frequencies, and the pure frequencies in turn will give us the possibility of using the Fourier transform. So we are already in a very good shape. So maybe I also would like to mention that so far we have reduced our considerations to a finite dimensional setting to avoid convergence issues and so on. And we are close to convolution, but it's not yet the convolution that you would use for finite vectors, which are convolution in the spirit of cyclic convolution. So yes, convolution can be done also in a different way, and I think it's good to take a short break now, if it's fine with you, and I would like to stop the recording now and continue later on. Okay, just because we have already studied some of these systems, I would like to give you an example of such a linear system, and the question is it, for example, a translation invariant system, and can it be inverted? I'm talking about the situation which is not solved by the Fourier transform, but in this case just by finite dimensional considerations, so using the matrix representation. So the system is the polynomial p of x is going to the polynomial q of x described by taking 2 times the derivative plus the polynomial shifted by 1 minus the second derivative. Now, there are two questions. What in this case is the linear functional, and what is the matrix representation? Now, I was using the translation operator here to describe the middle term. I was writing the inverse operator here, and in the same way I was writing the differentiation operator and the minus differentiation operator. And what you get here is, I think that's made not a good representation. No, I'm sorry, I probably, yeah, I see. Yeah, this is not, this is the wrong one. So unfortunately, I'm sorry, you don't see the matrix representation here. I was making a mistake here. I have to do it once more. and correct this term. But what you can see here, what I observed by doing such a thing, and you just take yourself some derivatives, some shift operators or so. If you apply these operators to the monomials, so let's say x to the third power, then you will get some first column. And in this concrete case, the derivative, and even more the second derivative, doesn't have any cubic term. And shifting a cubic term like x0 will give you, by binomial theorem, x third power plus something else. So there will be always a 1 here due to this main term and the fact that all the other terms are only happening in the lower part of the matrix representation. So because you have 1 times a shifted version, in this case you have 1, 1, 1, that this part is correct, the rest should be corrected somehow. And in this way, any such system which leaves the polynomial in some form will have will be invertible. It's different, however, if you would take, 2 shifted versions of the function, because then if they have the same leading factor, the cubic term may disappear, which means that the cubic functions are mapped into quadratic functions. So just take, I don't know, derivative, second derivative, any such thing alone without the original part would give you something which has a defect. So a non-trivial null space, for example, constant parts would disappear, and therefore you would not have invertibility. Okay, so the explanation here is not really useful. And I also tried to do another system, which was the one which I used for the MATLAB plot, applying to x third minus x, to GeoGebra demonstration, and tried to verify it by matrix multiplication. So recall the coefficients of x third minus x in MATLAB monomial basis, so to say, is 1, 0, minus 1, 0. So minus 1 is the scalar factor in front of the term, the linear term. There are no quadratic and constant terms and so on. And if you apply the correct matrix, not maybe the one above, you are getting exactly the polynomial, which should be this, but I think I have done some confusion. Okay, so this is maybe a good point to switch over from the consideration of cubic polynomials to the actual interesting part, where this would be a motivation. And this is the situation of continuous non-periodic signals. So I would say if you do Fourier analysis, the classical approach is to do it by talking about periodic functions. These periodic functions have a discrete set of pure frequencies, and you get Fourier series expansions. But real signals are rarely periodic. And even if they are periodic, maybe you have different periods that are not compatible. On the other hand, if you are having discrete signals, it's very easy to describe a signal by the real impulse response, because the delta zero is, okay, I hope you can hear me now. Is anybody else having problems to hear my voice? Okay, somebody else is saying it's okay, yeah. So I'm not sure, but it seems to be on a particular receiver. Sorry, Antis. I will try to record and you can take a look at the recording, yeah. Okay, so the reasoning why I don't want to have periodicity is because it makes the Fourier transform kind of easier, because you have just individual frequencies and you can add up the frequencies. We would like to have the discussion where the Fourier transform allows a continuous frequency spectrum, and this continuous frequency spectrum will make Fourier inversion a little bit more tricky, but also more interesting. The other thing is I don't want to have discrete variables. That's the same thing on the time side now, but continuous variables. And actually the description of the things that I'm doing for the Euclidean case, so for our D is the dimension, with a focus on D equal 1, you think of audio signals, D equals 2, you think of images, D equals 3, you think of voxels approximating volume data or so. So these three situations described in an abstract way, and abstract means not meaningless, but without taking care of individual coordinate systems and so on, will provide a good approach to BIBOS systems. Actually, if somebody is interested and knows already BIBOS system a little bit, and you find a critical comment on how systems are described in the engineering books, including very good ones, very established ones, in the article by Michael Anser, which has appeared recently a few days ago in the arXiv. So this article is giving some representation. I would claim that my course is covering the same topic, even with much less effort, in the sense that he is using Schwartz distributions and Lebesgue integration, whereas I try to do it completely in a completely naive and kind of abstract way with very concrete background, which hopefully will help you also to do numerical implementation. So now I'm switching from cubic polynomials to a typical functional analytic setting. Again, I will describe the principles of functional analysis as we go, so you don't have to worry too much. Just recall that we are looking at C0 of RD. So maybe think of 2D. So you have images, gray level images, if you think of real valued versions of it, which decay at infinity, which means if you take a large rectangle or large circle, then outside of this ball, the function will be rather small. So if it's continuous, it's like a landscape for T2 over the thing, or a pixel image, but in a continuous version or so. Now, let's say you are interested, because you are interested in image processing, in a procedure which is doing edge detection. If that's supposed to be a linear operation, you would not like to say it has to behave on coordinate or on pixel number so-and-so in this way and at a different position in a different way. It should be just one procedure which helps you to recognize where you find an edge. So it's the same like a jump detector for time signals. So what is a good first or a simple naive way? You take the value, the difference between two neighboring values. We would say it's delta of 1 minus delta of 0. And if you go over the time signal, and if you record that this difference is big, that it means the function must have a jump. Now for 2D, you find a Laplace operator, something like this, which is just a functional applied to pixel images or to functions of two variables in a continuous way. And again, it's good to distinguish between functionals, operators, and signals. I will use these three names. So now we switch from our primitive prototypical collection of signals, which were the cubic polynomials, to the continuous functions, complex valued or real valued if you want, endowed with the sup norm, because whenever we are working with not anymore finite dimensional space, we have to deal with convergence, with approximation, and so on. Actually, on every infinite dimensional space, as we call them often, you can find operators which are linear but kind of nasty, which are not satisfying the so-called boundedness condition, which is 28. So in order to avoid pathologies in our setting, we are asking to have a bounded linear operator. And the bounded linear operator means you have a constant, depending of course on what kind of operator you give me, such that for every f in C0, the maximum is controlled by a constant times f. So we will have a lot of such operators. For example, you shift a function, then of course the shift is like drawing, you've seen the red example some time ago. I'm changing the time parameterization, but you would have the same curve, therefore shifting an operator doesn't change this. If you would say, well, I'm looking only at differentiable functions and I take the derivative, you would have a hard time to verify this. So taking derivatives, either it's not possible for every element in this setting, or you take a smaller space, but you still use the subnorm, it would not be bounded. Okay, and then of course, we are assuming that it's commuting with translation. So you would like to know that the output of the operator is independent of the time shift if you do the time shift before or after the operator is the same. Now, for me, this definition is the elegant definition and the correct description of BIBOS system, and BIBOS stands for time bounded input, bounded output systems or so. You can have many variations. For example, and that's a little bit what also Michael Unser is doing here. You can, for example, say, well, you have an operator which maps C0 into C0. It has some very simple-minded, harmless extra properties. And it has the property that the output of any bounded input signal is a bounded output. So kind of taking the word BIBOS more literal, not saying I control the size with a uniform constant. So it's a magnification factor, so to say. The output is at most 5 times as big as the input if C equals 5. No, it would just say, if you give me any input, you have any output. But very weak assumptions imply, usually it's called the closed graph theorem, that if you have only for all the elements of this complete space, of this Banach space, that the input is bounded, the output is bounded. If the input is bounded, then you must have such a constant. And this principle is essentially that if you would have an unlimited relationship, I mean unlimited magnification, you would be able to fabricate the function with all the nasty guys, and then the output would not be bounded for this particular function. And so it's the completeness of these spaces which tells you that this is actually not such a bad idea. It's a very reasonable, very good, very useful practical condition. Now, C0 is the space of all functions which vanish at infinity. So you can neglect the part at infinity without losing too much information. And therefore, I find that the next part is a little bit more realistic for testing. We call that C sub C is the space of continuous function with compact support. So, I mean, in real life, nobody can test functions with 300 years of input. You would test for signals which have maybe 3 minutes, 1 minute, 10 minutes or so. And then you are looking at the output, T of F. And the claim is, if you look at the last line, that for any finitely supported input, you are looking at the output, and you must only know, or somebody has to guarantee you that it's reasonable that if you're taking an interval which is rather long, so inside, actually I might write better y here in the last line, 31. If y is larger than r, then the output T of F at y should be less than epsilon. So kind of, I would call these systems real, I mean, not in the sense of quantum mechanics, but in the practical sense, observable signals. That means you can test them by putting input and later output. And you watch them for a while, and maybe because of the smearing effect, you have some delay or so. So you're shaking your instrument with some profile, and you see that it starts vibrating, and then with damping after a while, it's going to 0. Then you're having another profile and another profile. And then you're saying, well, I have enough information to approximately reconstruct the convolution kernel which describes this system. That's more or less the goal. And the idea of the frequency description would be that you would say, well, I'm testing it against pure frequencies. And in practice, you would say, well, I have maybe a mechanical object, and I start vibrating at different frequencies. And if somebody is saying, well, now be careful, now it's kind of starting to resonate and to vibrate more and more, then maybe you have hit a resonance frequency, which we will see is a place, a frequency, where the Fourier transform of the impulse response is getting larger than 1. So doing it for a long time will lead to an explosion of the system or something like this. And of course, let's say in a train which may start to oscillate, we want to avoid this, or we want to understand this mechanical system so that there's no problem. So here you have the link to this other thing. I will now switch to the back to the script and hope that this second definition is not part of the script at the moment, but later on I will insert it. So the script, please confirm in the chat that you see now the script with the lemma 3 more or less, if somebody can. Okay, thank you very much. Okay, so I will not redo things which we have done already, but recall the spaces that we have used, the uniformly bounded continuous functions and the functions vanishing at infinity, both sitting inside the space of bounded continuous functions. When we talk about convergence, we take subnorm convergence, which means two functions are very close to each other if you have for real and imaginary part an epsilon strip that contains the other guy here. So uniform convergence of any sequence guarantees you that the limiting sequence cannot be a step function. And that's actually one of the problems that we will have and see in Fourier analysis. If you recall, and you have certainly heard about the Fourier series expansion, which is in terms of pure frequencies, every pure frequency and therefore every trigonometric polynomial, so any finite linear combination of pure frequencies, will be a continuous function. If somebody wants to approximate a unit step function or a rectangular box function by pure frequencies, you will have a hard time to do it in a uniform way, because clearly at the jump, the approximation tries to be at the top and at the bottom at the same time, which is of course not possible. So you will have problems with uniform convergence if you're near the jump. But the actual situation is some overshooting and the so-called Gibbs phenomenon, and that you can analyze it very much, has a lot to do with compressed sinc functions, which we will see later. Recall also that we have seen that pointwise products of uniformly bounded continuous functions are again uniformly bounded and continuous, or if you multiply a function vanishing at infinity with a bounded continuous function, then you will get a bounded continuous function. This term has been corrected meanwhile. So just to illustrate here, a good example of a function is the real part of the chirp signal. So acoustic version of the chirp signal, we will see a spectrogram at some point later on, would be, so linear frequency chirp is like, and your ramp have a linear ramp in the spectrogram. Now, if you multiply this with a harmless bump function, I'm showing you only the positive part, 1 over 1 plus x squared, one of the few guys who has really a nice Fourier transform, you see very quickly that the damping of this C0 function makes this oscillating function quite nice and small, which is in C0. Now, the guy which is in C0 is uniformly continuous. Somehow, why? Because if you're testing uniform continuity, you will see everything is small, also differences are small if you're close to infinity. So you look only at the steepness in the finite part, and any function which is continuous is uniformly continuous on any finite or compact part. So C0 functions are uniformly continuous. The pure frequency, I didn't plot that, of course, is not decaying at infinity, but it's uniformly continuous. Very clear, because the derivative of cosine is sine, more or less, and sine never exceeds the absolute value of 1. So pure frequencies are in UB, but not in C0. And this chirp guy is bounded, continuous, even smooth, but it's not uniformly continuous. Because if you're giving me any epsilon which is harmless, like epsilon 1/2 or so, and I try to give you a delta, you can always go to infinity and say, well, I find a delta interval close to two functions at infinity which are closer than a delta, but one has the value +1, the other -1. So it's not uniformly continuous. Another thing which I want to explain or repeat quickly is we are using this symbol of a triple par for the operator norm. So the operator norm with respect to the sup norm is that you're comparing the size of the output with the size of the input. So the condition that we have seen just before with there exists a constant means that this operator norm is finite. So we just take, you could say, we take the infimum over all the possible constants that you can take. So it's the smallest possible control for the magnification factor. So maybe we should write here also that this number, the operator norm of t with respect to the sup norm, is the smallest number that allows you to control the size t of f by this particular number times the size of the input. Now, I don't want to do too much functional analysis so early, but I would like to recall that if we go from signals, so to say, which we have now with C0 and so on, to operators, you also have nice Banach space structures. So you can say, well, this expression is really measuring the size of an operator. Identity, of course, has size 1 because input and output are the same. 3 times identity has norm 3. Diagonal operator, which maybe stretches some parts and the other parts are compressed. The bigger one is the upper norm, and the smaller norm is controls the inverse operator, for example. And so we can say we take all these linear bounded operators. So I use the symbol L. Sometimes people use B for bounded operators from C0 to C0. So on the space C0 of RD, endowed with this norm. So it's the long description and the short description is just 3 bars, is a Banach space. That means, first of all, and at the moment I would leave it there, it is a normed space. So if somebody says you have convergence of operators, some operator is close to another one, for example, a numerical implementation of an operator is close to a continuously described operator, then we will do this. We will also see that there are other ways of describing closeness, which is important when you are doing something like the continuous Fourier transform and you want to approximate with the FFT, which is a priori a very hard task because you're defining an operator on infinite dimensional spaces and you want to approximate it by finite dimensional spaces or matrices which have different size. So how can matrices of different size be similar to an object which is also not a matrix even? We'll see how to do it. What is clear is that the composition law is compatible with the size measurement. Of course, again, there's a typo. It should be T2 here. So if you combine 2 operators, the resulting operator norm is at most this. This is actually the same situation that we have with the norm of matrices. So you can play around yourself with MATLAB. If you take the norm of a matrix, you're getting this triple norm that we have here, the best possible constant that allows you to control the size of A star X with by the size of the input. So usually I would do now a GeoGebra demonstration and say, well, you're giving me maybe a symmetric 2 by 2 matrix. And then we know a symmetric matrix, real symmetric matrix, can be diagonalized. So if you're asking me, what are vectors of length 1 doing? We all know that by rescaling it's enough to take the unit circle. So we take only vectors of length 1. So you should think of a or a set of vectors pointing to the end with their endpoints on the unit circle. Now with GeoGebra you can move such a vector around, you can apply matrix, and you can watch what the output is, and the output is an ellipse. So a 2 by 2 matrix maps a circle to an ellipse. A 3 by 3 matrix, which is symmetric, maps the sphere of the three-dimensional ball, the surface of the three-dimensional ball, into an ellipsoid, so like a cucumber or a zeppelin. Now the symmetry implies that actually the unit axis go to the main axis. Otherwise you have a different representation giving the same ellipse. So I stay with the symmetric case. So if somebody's asking, well, how long can a vector be? Then you look at all the directions and you see that they are all ending up at points of an ellipse. So it's clear that the biggest axis of the ellipse, the main axis, is describing you how big, what's the worst scaling factor. So that's actually how MATLAB, and you should look up the details in MATLAB, is computing the norm of a matrix. It's just doing a singular value decomposition. So essentially it's determining for symmetric matrices the eigenvalues of the matrix, and it's saying take the absolute biggest one. So maybe you have eigenvalues -3 and +2. Then of course the absolute value of -3 is +3, is the biggest one, that's the longest axis, and such a matrix would have norm 3. So it's clear that also this norm, which would be the magnification control in the Euclidean setting, and that's the usual operator norm, would be exactly something having exactly the same property that we have now with this situation here. I'm jumping and leaving out this part here and try to come to the, we will not do all these, we will do some of these things, but we will skip most of them. I'm sorry, I have to find the representation of systems. So should have prepared that. Yeah, okay. Yeah, so the representation of system will have to do a lot with linear functionals. So now I will try to talk a little while about measures. So we are at page 21, and we start with a harmless definition. I would just say, I don't care about the linear functionals on this, how they look like, but probably if you have understood the cubic polynomial case, maybe we can represent these invariant functionals by linear functionals on the space C0. So I will use the symbol M for bounded measures, M for measure. I think actually most of the time I will use MB to emphasize that these are the bounded measures. Now, a priori, the term measure is coming in from a completely different context. I will try to tell you a story now, or maybe show you a motivation, and you can read some more details here. So I was already indicating here that in measure theory, people will say, if there's an abstract measure, then we can write integrals. And that means if somebody, think of some measure on R2, that's something that tells you how big are rectangles. Now, if somebody is giving you rectangular and somebody is showing you a Lego landscape, so a collection of boxes, then you would say, okay, this landscape has a total volume, which is of course the size of the basis, so that's where you need to measure. So let's say the ground area measured in a particular way is 5 units, and the height is 2. Then of course you multiply 2 by 5, and you have that this parallel box has the volume 10. And then you're taking another one, which is a little bit larger, but the amplitude is lower. So for step functions, it's very plausible what the integral should be. But in contrast to the Riemann integral, where you say now if some function is the limit of step functions from above and from below, and if the two procedures give you the same thing, Lebesgue has invented a more sophisticated way. So he was concentrating on, so to say, more complicated shapes of those functions. So essentially, I would say in a two-dimensional situation for me, a good description of the ideas of Lebesgue would be to say, well, a two-dimensional function is like a mountain, a model of some mountain. Now you make contour lines. So you say, well, you make steps of only 10 centimeters or so. And so then you see closed contour lines around those hills, which are here. And then you do it like Wachau or Dürnstein in Austria, these vineyards. You make step functions, but you keep them constant. And then you say, if I can measure the area at each level, I multiply with the height at which this level occurs. And then I try to take the limit. And surprisingly, his integral terminology is much more general than the Riemann integral, at least for people who like theory. The other thing is the term of a Riemann-Stieltjes integral, which I was slightly indicating earlier. Here you would say, well, Riemann integrals say you take an interval on the one-dimensional case. You take an interval and you divide it into boxes of size x5 minus x4 and so on. And normally you would say I take one value from the interval, the biggest one, the smallest one, the midpoint, the corner point, whatever, some point. And then you take the length of the interval. Yeah, I will give a description of finite measure in the formal way just right now. Okay, so first I finish this here. So the Riemann-Stieltjes integral would be that you're measuring the length of an interval in a more abstract way. I mentioned the word monotonous function or difference of monotonous functions as a function of bounded variation or so. So in this way, you can define either a measure or you can define integrals. Now, if I say bounded measures, because this question came up in the chat, I can give you a right. If you're knowledgeable in measure theory, it will say, if you think of a positive measure, you can say, we are on an unbounded domain, Rn, Rd, or the whole real line or so. And a measure, of course, should assign to an interval or to a square or to a cube a finite volume, but it may increase if you make the intervals bigger and bigger. And so a finite measure as a bounded measure will be a measure while you have a constant, independent of the size of the thing. Now, my definition is completely harmless. I'm just calling something a bounded measure. If it's a bounded linear functional, and maybe I should add some comment here, the dual space is always the space of bounded linear functionals. So you're saying, I'm looking now at all these objects which I have called sigma in the cubic case. Now I'm referring to measure theory, I call them mu, but I ignore the details of the representation. And I would say measure theory grew out of the fact that if you try to do this Riemann-Stieltjes integral in 2 dimensions, then in 3 dimensions, it's getting more and more cumbersome. And the basic observation was, well, first you have to know what the volume is, let's say, of a rectangle. And you use divided differences of some function, which is like this capital F. Once you have this, the rest of the machinery is more or less automatic, lengthy, elementary, and time-consuming. And I'm taking not the measure theoretical point of view, but the so-called integration theory. Let's assume somebody was smart enough to invent such a functional. We will use it, and I don't care. And I like to compare it with mobility again. Maybe, I don't know, 30 years ago, mobility was the same as, and supporting mobility was like building good cars, building good streets. Nowadays, we know maybe shared electro cars are the right thing. So we don't care about the inessential part, the technicalities, but of course we care about mobility. So here we want to integrate things, but whether it's a Riemann integral, a Stieltjes integral, a generalized function applied to a test function, this is in a way more flexible, but less kind of technique dependent. Okay, so, and I must say in Fourier analysis, and that's the subject of the course, very often there seem to be good arguments why we should study first L1, which actually turns out to be a closed subspace of the bounded measure. So we'll see in a while, very soon, that L1 functions are just the so-called absolutely continuous bounded measures. But my point will be for a little while to convince you I can work with these bounded measures without knowing what they are. So what is a measure could be viewed almost as a philosophical question. My favorite comparison, kind of in real life, is the statement, I can tell you or somebody can explain to you what healthy life is, even if you don't give a formal correct definition of what health means. So I will tell you how to work with bounded measures. I will give you a lot of ideas, and maybe I give you more useful hints without connecting it with measure theory. Of course, if you read mathematical books, you will see a lot of measure theory. And if you look at some of the engineering books, actually the majority, I would see sometimes a little bit of mystification with the Dirac measure, sometimes a little bit of hocus pocus with symbols, which are integrals, which shouldn't be integrals. So I try to avoid writing integrals when they are not real integrals in the spirit of at least Lebesgue, and actually most of the integrals that we will see are Riemann integrals, and I will be careful about the distinction. Okay, now there's a lot of text which I can skip. Yeah, maybe the point of a positive measure of measures is first you define that you're saying, well, I measure the size, so the size has to be positive. So people would say in measure theory, I'm talking about positive measures. So what is a real measure? Well, it's a difference between two positive measures. What's a complex measure? Well, it's a real plus I times an imaginary measure. Well, that you can decompose every such functional into a positive and a negative and a real part, imaginary part, and then you come up with the absolute value is something which is a little bit difficult with my approach, but I think you don't, will not need it very much. So let us jump right away to the examples. So we have, as we had before, mapping from Rn to R, we have linear functionals are from the space, which is now the space of C0 functions, into the underlying field. So it's real numbers, complex numbers. And what is the most basic one? It's very simple. If you take a continuous function, you have f of 0. If you want to have a Dirac at another point in Rd, you just evaluate at this. Is this a linear mapping? Yes, of course. Is it continuous? Well, it means, can you control the size of the output? So if somebody is giving you, I don't know, u equals 5, please evaluate every function at 5. I mean, by definition, clearly the value at 5 is at most, in terms of absolute values, at most the sup over all the values. So the estimate is these functionals all have an estimate by the constant 1. Can you do anything better? No, because it's very easy to take, I don't know, a triangular function which is equal to 1 exactly at the point u that is interesting for you. So every possible constant which might be less than 1 will not be useful. So in this way, I have already explained to you what I put as an exercise here after 48. So the formal definition of the size of a functional, very much like the size of an operator, is, well, what is a functional? A functional on C0 is something that maps continuous functions in C0 into, let's say, complex numbers. So mu of f are a bunch of complex numbers. By assumption, if you take all the elements from the unit ball, these elements are inside some circle, and you take the smallest circle containing all these elements, or the sup over this. So you see here, if you take equal to 1 the size or less than 1, I mean, if you give me an element with maximal size, let's say 3/4, of course it will have as output 3/4 of the output. The size will be 3/4. So every direction, so to say, means every element which has this norm equal to 1 can control the smaller versions of it. So this is really how you measure the size of a bounded linear functional. And as I was giving you the explanation, the Dirac delta, please don't call it function from now on, but we call it point measure or Dirac measure. Sometimes you can also call it a Dirac distribution or so, will be the evaluation, and every u or t or whatever you take is such a measure, and it has norm 1. Now, I think we are close to the end of our session, and so maybe I just indicate where I will start next time. That if you are giving me any finite linear combination of Diracs, so the measures are again a vector space. They're actually also a Banach space with this norm, and so maybe I should add some comments in this direction also. But then we can say any finite linear combination, and I like to use now K in F and capital F for finite set. So you give me 20 points, 20 coefficients, and you are doing this linear combination. Then, of course, there's a canonical representation. You should not write it as, I don't know, 3 times delta at 1 minus 1 times delta at 1. Then you would say, no, 3 minus 1 is 2. So make distinct points here and take the coefficients of those distinct points. Then you have the so-called canonical representation. And we will take a look why for this canonical representation you find out that the measure norm, so the size of this, which has to be finite, of course, is exactly the total norm of the coefficients. So somehow you can think of point mass is located at positions tk over a finite set that can be finitely many points in the plane, for example, and they have coefficients. The total mass of any complex or real valued is the absolute value of the amplitude, and so we will check that you can determine this norm, and it's this number. And I think this is a good point to stop my presentation and to thank you, and I'm available for questions now. So thank you for today.